Assalamualaikum warahmatullahi wabarakatuh. Thank you for the opportunity. My name is DINDA ULIMA and I'm going to present my research called Markov Switching GARCH-Machine Learning for forecasting return volatility. Financial market volatility prediction has many important applications in risk management and portfolio selection. Financially, seen over the long term, many things can cause behavioral changes in financial data, such as natural disaster or changes in government policies. So the assumption that variance of financial data remain the same over time become unrealistic. The general autoregressive conditional heteroscedasticity or GARCH model was developed to overcome the possibility of non-constant variance. However, nonlinearity problem often occurred in asset returns, especially in the literature on volatility modeling. Machine learning methods are used to solve this problem. Various studies have been conducted to predict the volatility of financial assets by combining the GARCH-type models with machine learning, especially neural network. In several cases, there are structural changes in the volatility of financial data, and the GARCH-type model may fail to capture this volatility movement. One way to overcome this problem is to allow for variation in the GARCH parameter, like in the Markov Switching GARCH model, which allows for different GARCH behavior in each regime to capture variance in high and low volatility periods. Markov Switching GARCH model can have more than one different GARCH behavior, where each GARCH model follows a certain distribution assumption in obtaining parameters estimates. However, sometimes the distribution of financial data and return volatility may be unknown. The Markov Switching GARCH-Machine Learning model is proposed to capture the shift in the volatility regime without being limited on a certain assumption. This study aims to predict return volatility based on the volatility on each regime using machine learning algorithm including support vector regression and long short-term memory. Christian Puller and Minutulo in 2018 analyzed Bitcoin volatility forecasting using a combination of several GARCH-type models with multilayer perceptron. Kim and Won in 2018 and Liu and So in 2020 combining GARCH-type models with LSTM to forecast volatility on financial data. Ardia et al. In 2018 and 2019 compared the performance of the single regime GARCH with the GARCH model, which involves a Markov switching mechanism. Liu et al. In 2020 combining Markov switching beta TE GARCH with multilayer perceptron, and Tahiri in 2021 analyzed the return volatility forecasting using backpropagation based on the estimated volatility of the Markov switching GGR GARCH. The data used in this research is the daily Sukuk closing price on the trading day from Franklin Global Sukuk von Luxembourg. The data is divided into in-sample and out-of-sample data. The variable used in this study is Sukuk return, which is calculated using the equation 1. The volatility of Sukuk return is not observed directly, so a proxy is chosen to represent the actual value of volatility called realized volatility. In this research, the squared return is used as the realized volatility. In Markov Switching GARCH model, let RT be the return value at time t. RT is assumed to follow the normal distribution, have zero mean, and serially uncorrelated. This assumption means that the MS-GARCH model is carried out under the mean time series AT written in equation 4. The conditional variance of RT following the MS-GARCH-11 model with two regime written in equation 5, where sigma squared subscript t-1 is the expected variance at time t-1, and st follow the Markov chain process with two-state space, where st equals to 1 represent the low volatility regime, and st equals to 2 represent the high volatility regime. St is unobserved, but the probability of a transition from one state to another can be known through the transition matrix. The expected variance sigma square subscript t is written in equation 6. This expected variance formula is used as an input for the machine learning model. The mean time series used in MS-GARCH model is obtained from ARMA-based machine learning model. The process of obtaining the mean time series for the MS-GARCH SVR and MS-GARCH LSTM is carried out separately. The mean time series for the MS-GARCH SVR model, called AT-SVR, is obtained from the residual of ARMA-based SVR model, or the SVR model with input specification following the ARMA model. Meanwhile, the mean time series for the MS-GARCH LSTM model, called AT-LSTM, is obtained from the residual of ARMA-based LSTM model, or the LSTM model with input specification following the ARMA model. The steps for predicting the volatility of sugar return using MSGARCH SVR are: estimate the mean time series AT-SVR, estimate the probability and volatility of regime 1 and regime 2 from AT-SVR MSGARCH, modeling SVR with input probability and volatility of regime 1 and regime 2 obtained from step 2, turn C parameter to get the optimal MSGARCH SVR model, estimates in-sample and out-of-sample volatility using C parameter from step 4. The step for predicting the volatility of sugar return using MSGARCH LSTM are: estimate the mean time series AT-LSTM, estimate the probability and volatility of regime 1 and regime 2 from the AT-LSTM MSGARCH, modeling LSTM with input probability and volatility of regime 1 and regime 2 obtained from step 2, using several hidden neuron. Choose MSGARCH LSTM model which gives the smallest error. The result of AT-SVR MSGARCH and AT-LSTM MSGARCH each produce probability and volatility of regime 1 and regime 2. If the probability of regime 1 is high, close to 1, then the volatility is in regime 1. Otherwise, if the probability of regime 1 is low, close to 0, then the volatility is not in regime 1. The same goes for regime 2. For in-sample data, AT-SVR MSGARCH model in green line produce almost constant low volatility forecast, while the MSGARCH SVR model in red line produce a volatility forecast value that is slightly higher than the realized volatility that has shown increase at several points, although the increase is not as large as the realized volatility. AT-LSTM MSGARCH in yellow line shown an increasing pattern follow the realized volatility, while the MSGARCH LSTM model in blue line produce higher volatility than the realized volatility and tend to be at the same level over time. For out-of-sample data, the MSGARCH LSTM model in blue line produce higher volatility than the realized volatility and tend to be constant over time. The MSGARCH SVR model in red line has shown small increases and decreases similar to the realized volatility, but has not been able to capture a very high increase in volatility. Kim and Won, on their research in 2018, found that the standard model that is widely used to estimate the volatility of financial sector, especially the GARCH-type model, reflect the empirical characteristic of in-sample data, but these empirical characteristics are difficult to establish on out-of-sample data. The result of this study is similar to what Kim and Won found. The MSGARCH model used in this study, both using the mean time series AT-SVR and AT-LSTM, estimate almost constant volatility prediction of out-of-sample data. The accuracy of the model is measured using mean square error. For the in-sample data, AT-LSTM MSGARCH produced the smallest MSE, while for the out-of-sample data, MSGARCH SVR produced the smallest MSE. The accuracy of a forecast can only be determined by considering how well a model performs on new data that were not used when fitting the model, so that MSGARCH SVR has the highest accuracy since it gave the smallest MSE on out-of-sample data. The MSE of MSGARCH SVR is smaller than AT-SVR MSGARCH for both in-sample and out-of-sample data. This result indicates that the SVR method is able to increase the accuracy of MSGARCH model. MSGARCH SVR also gives a smaller MSE than MSGARCH LSTM for both in-sample and out-of-sample data. Indicates that SVR can predict the volatility of sugar return better than LSTM. The MSE of MSGARCH LSTM is still greater than the AT-LSTM MSGARCH for both in-sample and out-of-sample data. This indicates that the LSTM methods doesn't improve the accuracy of MSGARCH model. The conclusion of this research are: the MSGARCH SVR has a better performance than the other model in forecasting volatility because it gives the smallest MSE on out-of-sample data. MSGARCH SVR is better than AT-LSTM MSGARCH, and MSGARCH SVR can model the volatility of sugar return better than MSGARCH LSTM. Overall, the MSGARCH SVR model is better than the other model. This is the reference used in this research. And this is the end of the presentation. Thank you very much, and wassalamualaikum warahmatullahi wabarakatuh.